Okay, let's proceed from the starting point. Uh, when does IR when to absorb IR radiation occur or to absorb infrared absorption? Firstly, IR absorption only occurs when IR radiation interacts with a molecule undergo a change in dipole moment, as it vibrates or rotates. That means when is a IR radiation bombard with a molecule that changes a dipole moment, the molecule that absorb uh, infrared radiation, and unless and otherwise, when there is no dipole moment change, when infrared radiation interacts with the analyte, there is no uh, IR absorption. Secondly, infrared absorption only occurs when the incoming IR photon has sufficient energy for transition to the next allowed vibration state. ይህ ማለት ደግሞ ወደ ኔክስት ያለውን ትራንዚሽን ሌቭል ማካሄድ የሚችል ኢነርጂ ሪሊዝ የሚያደርግ ወይም ኢነርጂ ሲይዝ ነው ማለት ነው። ኖት if the two rules are not met, no absorption can occur. Not all bonds in a molecule are capable of absorbing IR infrared energy. Only those bonds that have change in dipole moment are capable to absorb IR radiation, because IR radiation are absorbed only when there is dipole moment. That dipole moments come from their partially negative and partial positive of the interacting atom or element. Through that there is a dipole moment because of their electronegative and electropositivity. The larger the dipole change, the stronger the intensity of the band in an IR spectrum. Dipole moment means the measure of net molecular polarity in a chemical bond or molecule, and equal to the product of one charge and distance between the charging atom or element. This means dipole moment measures the molecular polarity of the compound. For example, water is the combination of oxygen and hydrogen. Oxygen is partially negative and hydrogen is partially positive. Through this there is a dipole moment because of different electronegativity. This results to the observation of infrared light. Many molecules have such dipole moments due to non-uniform distribution of positive and negative charges on various atoms. As we have said, there is different electronegativity and different electropositivity. This results net dipole moment change አለ ማለት ነው። እንዴት ኮምፓውንዶች አይአር ራዲዬሽን አብዞርብ በሚያደርጉበት ሰዓት ኔት ዳይፖል ሞመንት ያመጣሉ። ይሄ ደግሞ ለአይአር አብዞርቤሽን እንዲኖር ያደርጋል ማለት ነው። In heteronuclear diatomic molecules, because of difference in electronegativity of the two atoms, one atom acquires a small positive charge or partially positive and the other negative charge partially negative. This molecule is then decided to have dipole moment whose magnitude is dipole moment equals to charge of the interacting atom times the separation distance between the two interacting atoms. Many molecules have such dipole moments due to non-uniform distribution of positive and negative charges on the various atoms. As we have said in the above, when the dipole moment change is greater, the absorption of infrared radiation is also greater. Molecular species that absorb infrared. Which molecular species or which part of the molecule that absorb infrared radiation? Asymmetrical stretching and stretching and asymmetric bending change the dipole moment of a molecule. That means if there is asymmetrical dipole moment or change, stretching or bending, there is absorption of infrared light. This means there is a net dipole moment ማለት ነው። Asymmetrical stretching or bending are infrared active because there is a dipole moment change, because one of the interacting atoms are partially positive and one of the interacting atoms are partially positive. As a result, there is net dipole moment change. Whereas symmetrical stretching or bending are not are reactive because there is no net dipole moment. Each bonded atoms are stretched equally or compressed equally. Through this, there is no net dipole moment. For example, as we see in this molecule, there is equal stretching or bending. As a result, there is no net dipole moment because the two interacting atoms stretch or compress equally in the same direction or in the opposite direction. Vibration of two similar atoms against each other, for example, oxygen nitrogen molecule, will not result in a change of electrical symmetry or dipole moment of the molecule, and such molecules will not absorb energy in the IR region because each atoms have the same or similar electronegativity, and that contributes with stretching power or compressing power. As a result, there is no net dipole moment. A molecule number of vibrational modes. A molecule consists of n atoms, has total 3n degree of freedom corresponding to the Cartesian coordinate of each atom in the molecule. In non-linear molecule, 3 of these degrees are rotational and 3 are translational, and the remaining corresponding fundamental vibration. Our target to get in this IR radiation is fundamental vibration. In a linear molecule, 2 degrees are rotational and 3 are translational. The net number of fundamental vibration for non-linear and linear R molecules. For non-linear, degree of freedom is equals to 3n minus 6 because there is 3 degree of rotational, 3 translational, and the remaining are fundamental. As a result, 6 of are minus or reduced from the fundamental. As a result, fundamental vibration are 3n minus 6 because the translational and rotational vibration are reduced. In the linear molecule, there is 2 degree of rotational and 3 translational. As a result, we subtract from the fundamental remains 3n minus 5. For example, calculation reveals that simpler molecules such as propane has 27 fundamental vibration, and therefore you may predict 27 bands in the IR spectrum because propane is non-linear, and 3n times 3n minus 6 means there is 3 carbon and 8 hydrogen. As a result, 11 atoms and times 3 33 minus 6 27 fundamental proposition. That means translational and rotational vibration ተቀንሶ ማለት ነው። But this number may be increase or decrease. There are factors that are affecting the increasing or decreasing of this number or fundamental transition. Reasons for decrease: 2 bands may overlap or degenerate. An absorption may not be in 4000 to 400 per centimeter range. That means በሚድል IR range ውስጥ ሳይገኙ ሲቀሩ ይሄኛው ዲክሪዝ ሊያደርግብን ይችላል። ሌላው ደግሞ an absorption may be too weak to be observed. ላይናችን ማየት ሳንችል ሲቀርና ሳንቆጥረው ስንቀር ይሄኛው ደግሞ absorption ባንዳችን ሊቀንስብን ይችላል። Absorption may be close to each other to resolved on the instrument. That means 2 of the bands are very close or too close to each other. They are not resolved by the instrument and considered as a one band. And lack of dipole moment, as we have said in the previously, to IR radiation to be absorbed, there is a net dipole moment between the covalent bond of the interacting atoms. And the factors that affect increasing of the numbers of the band The first one is overtone or multiple fundamental vibration or combinations, coupling or splitting of vibrational modes, combination tones to absorb simultaneously, and other factors that increase the number of bands in the IR spectrum. Molecules can vibrate in a variety of ways, but generally bond vibration modes are divided into two types. The first one is stretching vibration, and the second one is bending or deformation vibration. Uh, 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 Molecular vibration can be classified as we have said uh, stretching and bending, or stretching means back and forth, or lengthening or shortening of your bond length, and bending vibration are involves changing bond angle. And also stretching vibration can be classified into symmetrical and asymmetrical. The symmetrical are not IR active as we have said above, and asymmetrical are active IR active because there is any dipole moment. And bending vibration can be classified into two, in plane vibration and out plane vibration. A stretching vibration where the atoms move back and forth as if they are joined by spring along a bond axis. It affects the bond length. That means it may be length or compress or extend ሊያደርግ ይችላል ማለት ነው. More energetic than the bending vibration. Divide into types: symmetrical and asymmetrical stretching vibration. Bending or deformation vibration. The second is the bending or deformation vibration. They are displacement occurring at right angle to the bond axis or bond angle change ማለት ነው. Affect the bond angle or affect the bond angle and require lower energy than stretching vibration. That can be divided into in plane bending vibration and out plane bending vibration. The in plane vibration that contain scissoring and rocking, and also the outplaning vibration consists wagging and twisting. The IR spectrum is basically a plot of transmitted or absorbed frequencies versus intensity of the transmission or absorbance. Frequency appears in the x-axis in units of inverse centimeter or wave number, and the intensities are plotted on the y-axis in percentage units. As we see in the picture, the spectrum are plotted absorbance versus wave number or frequency. This indicates that the instrument measures the absorbance or instrument of transmittance of the light and inversely relation to the transmittance of light. That means transmittance is equal absorbance is equal to minus logarithm of transmittance. This is the most commonly used representation and the one found in most chemistry and spectroscopic books. That means transmission versus wave number or frequency. The transmittance spectra provide better contrast between intensity of strong and weak bands. Therefore, we will use this presentation. That means the transmittance versus wave number or frequency that gives accurate contrast between the intensity of strong and weak bands. And because of this, most commonly used in a representation of IR spectrum. The IR spectrum octane plot as the transmission left and absorbance right. That means transmittance versus wave number gives a better contrast than absorbance versus wave number. The another topic is the position of absorbance band. The amount of energy required to stretch a bond depends on the strength of the bond and the mass of the bonded atom that are expressed by Hooke's law. That means when the bond between the bonded atoms are strong, they have higher frequency and needs higher energy to stretch, and the mass of the bond atom are high, there is the wave number of or the frequency of the IR spectrum is low. The equation relates the number of stretching vibration to the force constant of the bond and the mass of the atom in grams, joined by that the bond and the force constant is the measure of strength of the bond. The stronger the bond is, the greater the energy required to stretch it, because the stiff the bond is between the bonded atoms that require higher energy to stretch or bend. Because the stronger bond corresponds to tight spring, that means it needs higher energy to vibrate or bending. Frequency of the vibration is inversely related to the mass of the atoms attached to the spring. So heavier atoms vibrate at lower frequency. That is inversely relation. As the mass of the bonded atom increase, the frequency of the vibration is low or minimum, and as the bonding atom's mass is lower, the frequency of the vibration is much more increased. As Hooke's law states that frequency is equals to 1 over 2 pi c square root of force constant over reduced mass. As the mass of the interacting molecule increase, the frequency or the wave number of the IR radiation becomes decreased, and wave number of the IR radiation is directly related to the force constant. This means that the stiff the force constant or the stiff the bond between the bonded atoms, the stronger the wave number or the frequency. IR striking what does the frequency versus depend? Frequency or position of normal mode of vibration of two atoms held together by chemical bond depends on the mass of two vibrating atoms. Light atoms vibrate at a higher frequency than the heavier ones because frequencies are directly related to the force constant and inversely related to the mass of the interacting atom. The force constant of the bond between them and bond order. That means the relative stiffness of the bond. When the stiffness of the bond is higher, it needs higher energy to vibrate, and that gives higher frequency of the vibration. Triple bonds are stiffer or vibrate higher frequency than double bonds, and double bonds are stiffer than single bonds because the triple bonds are more stiffer than double bonds, and double bonds are more stiffer than single bonds. As a result, there is increase in frequency of vibration of stiffer atoms or bonds. Stronger bonds are absorbed at higher frequencies, as we see in this slide. Carbon-carbon single bonds that have a frequency or a number of 1,200 per centimeter, and double bonds have carbon-carbon double bonds have 1,660 per centimeter, and carbon-carbon triple bond have 2,200 per centimeter. That means as we increase the stiffness of the bond between the vibrating atom, the frequency of the vibrating atom also increase. From the single bond outside triple bond, the frequency of the interacting atom also increase. Conjugation lowers the frequency. That means conjugation gives a partial single bond or partial double bond. For example, isolated carbon-carbon single bond that have a frequency of 1,640 up to 1,680 per centimeter. When conjugated with other carbons, their frequency decreased to 1,620 to 1,640 per centimeter. and aromatic carbon double bond or conjugated approximately 1600 per centimeter. ሌላው carbon hydrogen stretching. Okay, carbon hydrogen stretching, that means the bond that have between carbon and hydrogen or single bond. Hybridization affects the force constant of K. Bonds are stronger in order of sp greater than sp2 greater than sp3. That means the more the s character, the greater the frequency or the wave number. Bonds with more s character absorbs at higher frequency. sp3 ch stretching just below 2900 per centimeter. sp2 ch stretching just below 3100 per centimeter, and SCP character SCPCH stretch at 3300 per centimeter because SCP have more 50% of S character. As a result, the absorb at higher frequency and increase to 3300 per centimeter. Bending motion occurs at lower energy or lower frequency than the typical stretching motion because of the lower value of bending force constant that needs a lower energy to bend the bond between the interacting atom. And also resonance also affects the strength and length of a bond, and hence its force constant K. Thus, whereas normal ketone has its K, its carbonyl stretching vibration is at 1715 per centimeter, and ketone that conjugated with carbon double bond absorbs at lower frequency near 1675 to 1680 per centimeter because the resonance effect of the carbon double bond or conjugation. This leads to the carbonyl carbon partially single bond, and that leads to decrease in frequency of the vibration. Resonance has the effect of reducing the force constant, and the absorption moves to the lower frequency because when the force constant decreases, the frequency of the absorption moves to the lower frequency because as the force constant increases, the frequency of the absorbing molecule or atom also increases because force constant and wave number or frequency are directly proportional to each other. As we see from 2-pentanone, there is only ketone group that have absorbed at 1720 per centimeter. When we come to resonance or 2-cyclohexanone, there is a resonance effect that reduces to the IR absorption at 1680 per centimeter. This is a result from the resonance effect. So resonance affects the force constant. As the force constant decreases, the frequency or the wave number of the IR absorption of a molecule also decrease. The other factor is the electronegativity of the two vibrating atoms or development effect also affects the position of absorption band. That means the more the electronegativity of the compounds that interact with another atom, the more the frequency of the vibration. For example, carbon hydrogen stretch that have a frequency of 2850 up to 2960 per centimeter. Oxygen hydrogen stretch that have 3590 up to 3650 per centimeter because oxygen is more electronegative than that of carbon. Carbon nitrogen stretch around 1350 centimeter per centimeter because the electronegativity of nitrogen is slightly greater than that of carbon, and that are range of frequencies in this range. The other is sodium, nitrogen, hydrogen stretch that have a high frequency of vibration between 3300 up to 3500 because oxygen is more electronegative than that of nitrogen. Carbon-carbon double bond that have a vibrational frequency of or wave number of 1620 up to 1680 per centimeter. This is low because of polarity difference, or there is no polarity or minimum polarity that results low frequency, and other factors. As a result, the electronegativity affects the vibrating frequency that have between the interacting molecule. As the electronegativity increases, the frequency or the absorbing or the vibrating frequency of the molecule or the interacting atom become more increased. Hydrogen bonding alters both stretching and bending vibrations. That means stretching vibration causes vibration to much more frequencies. The two longer wavelengths with increased intensity indicates band widening. As a result, stretching or hydrogen bonding causes the stretching vibration to cause a vibration to move at lower frequencies to longer wavelengths with increased intensity. That means as the wavelengths increase, the frequency of the molecule or the analyte also decrease and cause band widening or ይሰፋል ማለት ነው እንትኑ or bending vibration cause shift to shorter wavelengths or less pronounced than stretching vibrations. As a result, hydrogen bonding affects both stretching vibration and bending vibration. In stretching vibration, the effect is to the lower frequency and lower wavelengths, longer wavelengths, and also causes band widening. The band in the spectrum have much more wide than the separated alcohol or any other polar molecule. The intensity of an absorption band depends on the size of the charge, the change in dipole moment associated with the vibration, the number of bonds responsible for, and the concentration. As the dipole moment, the change in dipole moment increases, the vibrational frequency of the molecule also increases, and the number of bonds responsible for absorption have direct effect on the frequency or wave numbers of the molecule in IR spectrum. As the number of bonds increase, the frequency responsible for the vibration of the molecule also increase, because stiffer bonds are higher energy than that of less stiffer than. As a result, energy and frequency are directly relationship. As the energy required for vibration of the bond between the interacting molecule, the greater the frequency. And also the concentration affects the concentration of the analyte or the concentration of the interacting bond responsible for the absorption of IR radiation also affects the frequency or the wave numbers of the vibrating molecule. Dipole moment, the greater the change in dipole moment, the more the intense the absorption. The stretching vibration of an OH bond will be associated with greater change in dipole moment than nitrogen hydrogen bond because the bond is more polar. That means the electronegativity of oxygen is much greater than that of nitrogen, and results much or greater dipole moment change. As a result, the frequency of the interacting molecule or the vibration frequencies are increased. Consequently, the striking vibration of OH bonds will be more intense. Likewise, the striking vibration of nitrogen hydrogen bond is more intense than that of carbon hydrogen bond because of nitrogen hydrogen bond are more polar than carbon hydrogen bond because nitrogen is more polar than that of carbon. As a result, or nitrogen is more electronegative than that of carbon. That means there is electronegativity difference that leads to increase the frequency of vibration. Order of strength or polarity of interacting molecule or bonds. OH oxygen hydrogen bond greater than nitrogen hydrogen bond greater than carbon hydrogen bond. This is because of polarity or electronegativity difference, or partially negative and partially positive difference. The other is the number of bonds. The intensity of an absorption band also depends on the number of bonds responsible for absorption. For example, the absorption band for carbon hydrogen stretch will be more intense for a compound such as octyl iodide, which has 17 carbon hydrogen bonds, than that of methyl iodide, which has only 3 carbon hydrogen bonds. The number of stretching or bonds that are responsible for IR absorption increase. Also, the intensity of the absorption band also increase. Concentrated samples have greater number of absorbing molecules and therefore more intense absorption bands. Intensities are referred as strong, medium, or weak, or broad and sharp. In the next session, we are discussed about instrumentation of infrared or infrared instrumentation. For today's lesson, this is enough. Like, comment, share, and like, comment, share በማድረግ ተባበሩን።